Hi everyone, I'm going to talk about query minimization under stochastic uncertainty, and this is joint work with Stephen Chaplick, Magnús, Halldórsson, and Tigran Tonoyan. We are interested in problems with explorable uncertainty, so sometimes we only have coarse information available for the problem we are trying to solve, but we can obtain precise information for a cost. So one first example as a motivation is from distributed databases. So it's usually very expensive to ensure data consistency, and this is usually done using a master database that you query, or you use a distributed consensus algorithm. However, also when we don't propose this framework in which instead the updates are sent to everyone asynchronously, and each node maintains an interval where the precise information can be. And when a precise value is necessary, then we perform a query, but this is costly, so we want to minimize it as much as possible. Another scenario is for market research. The larger the sample, the more precise data you obtain, but also for a higher cost. And one final motivation is from rescue drones. Usually we want to send this drone to a remote location, ideally using a shortest path, but the travel time is uncertain due, for example, to weather conditions, and you want to minimize the communication because the communication is expensive with the drone. Now let's look at the sorting problem in this scenario. We want to sort n unknown numbers, V1 to Vn, but we know for each number we know an uncertainty interval that we are sure that the precise value lies on. And we can learn the precise value by querying the interval for a positive cost. We are interested in adaptive algorithms, so the queries are sequential and information from previous queries can be used to decide what to do next. And the goal is to minimize the total query cost. So for example, if you have those intervals in the real line and you query those red intervals and the precise values are like in those dots, then you know how to sort the numbers without querying those other intervals. However, the precise values are unknown, so we don't know which intervals we're going to query. So look, for example, in those two intervals here, and suppose you decide to query first the left one. It may be that the precise value is here, so you need to query the other interval as well, otherwise you cannot decide which one comes first. And it may be, however, that the value of the other interval is here, so it would be enough to query only this interval here. So usually these algorithms are analyzed using competitive analysis, which is a standard framework from online algorithms. And in this scenario, you assume that the precise values are defined by an adversary and you're analyzing the worst case behavior. So this is usually called query competitive algorithms. And sorting was studied before in this scenario. And there are two competitive deterministic algorithms and randomized algorithms with better factors. We understand, however, that competitive analysis is rather pessimistic. And in particular for sorting, there is only one structure that prevents us to obtain better factors. However, instead we may know a probability distribution on the information, so we may have a stochastic uncertainty. And then we will try to build a decision tree specifying the order for querying intervals, and we want to minimize the expected query cost. So now let's look at what this means. So suppose you have those three intervals, and suppose you have a decision tree that specifies that you first query interval A. So A is going to be the root of the tree, and now we'll look at the possible situations for the precise value of A. If the value of A is in B, then we have to query B as well, but we don't need to query C. This happens with probability, so then we have a child node with B. If the value of A is here in the middle, then you don't need to query anyone else to decide the order. And if the value of A is in C, then you have to query C as well. So if the probability for the segments in A is 1/3 in each segment, for example, Then the expected cost of the decision tree is the query cost of A plus 1/3 times the query cost of B plus 1/3 times the query cost of C. So the cost of a tree depends on the query costs, on the probabilities, but also on the structure of the intervals. There have been similar models proposed before in the literature, but we argue that they are essentially different to what we propose. First one is the stochastic programming problem. But there usually a solution can only contain queried elements or uses the expected value of the non-queried elements. And a more similar model was studied by Weld and by Yamaguchi and Maehara, but they only look for approximate solutions for the underlying problems, and they only gave us symptotic bounds on the number of queries. So I believe that the model proposes closer to query competitive algorithms because we look for the optimal solution for the underlying problem and we try to minimize the query cost. So just a summary of our results. For the sorting problem, we obtained a polynomial time algorithm for computing the best decision tree. However, the problem of finding the minimum item seems to be hard, which is surprising because minimum is usually easier than sorting, both, for example, if you know all the values or if you're assuming the adversarial setting. So it seems that the minimum problem has no optimum substructure, and we tried various heuristics without success. However, a decision tree can be represented in polynomial space, and the cost can be computed in polynomial time. So it's an open question if you have a polynomial time algorithm or if the problem is NP-hard or even Sharpe complete. But we got good approximation algorithms, in particular algorithms that have factor better than the adversarial lower bounds. Now I'm gonna focus my presentation on the sorting problem. So we have n unknown numbers, we know an uncertainty interval for each number, and we can learn the precise value by paying a query cost. But now we also assume a probability distribution of the values over the intervals. Some constraints we assume on the probabilities is that they are independent for different intervals. For any subinterval, we know how to compute the probability in constant time, and the information about the probabilities cannot be used to shorten the endpoints of the intervals. So the intervals are minimal regarding the information. So before we look at the algorithm, let's look at some structural properties for this problem. So the first one is if we have any two intersecting intervals, then at least one of them needs to be queried in order to decide the relative order. So we have an interval graph defined by this relation. And the second property is that if an interval like this red interval contains the precise value of another interval, then this red interval is part of any solution, so it has to be queried by any solution. And in particular, if it contains another interval, then it has to be also in any solution. So we can assume a proper interval graph, so we have no containments. Otherwise, we can preprocess the instance and query those intervals. So let's look at some insights for the algorithm. And suppose you have intervals like these. The first insight is that we only need to consider the segments defined by the endpoints. And in particular, we can assume with all loss of generality that the probability that a value falls in the endpoint of a segment is 0. So we can only we can only care about values falling inside the segments. So now let's look at what happens when an algorithm decides to query first an interval like this I3, this red one. And suppose the precise value is in segment X. So then all these other red intervals also have to be queried by any solution, and all other intervals are either to the left or to the right of the segment X. So we have two independent subproblems. And now let's look at what happens when we query those other red intervals. This will define what we call a cascading area, which is an area that contains all the precise values for those red intervals. and is minimal. And then we have a left subproblem and a right subproblem. So I'm going to put some indexes here. So the left subproblem is from segment Y to segment Z prime. The cascading area is from segment Z prime from segment Y prime. And the right subproblem is from segment Y prime to segment Z. So our algorithm is a dynamic programming algorithm. So we're going to compute a table M with parameters Y and Z containing the best solution, the cost of a best solution for all the intervals contained in an area defined by segment Y and segment Z, where A and B are the endpoints of a segment. So this set of red intervals, we're going to call it IX of Y and Z. So it's the set of intervals contained in this area that contain the segment X. And given this first interval we query and this segment X, the probability for a given cascading area, Z prime to B prime, we're gonna call it P with all these indexes here. So the table M, the value is 0 if the area contains less than 2 intervals, because one interval is trivially sorted. Otherwise, we're going to choose the best first interval to query, and for each possible segment, for its precise value, which happens with this probability, we query the set of red intervals, and for each possible cascading area, we have independent left and right subproblems, which I'm going to explain how to solve in a moment. So the probabilities can be pre-computed in time big O of n to the 4th, and the whole table can be computed in time big O of n to the 6th. So now let's look at the left and right subproblems. I'm going to present the left subproblem because the right one is analogous. So suppose you have the left subproblem, so you did not query these intervals yet, and you queried all other intervals to the right. And the subproblem has 3 parameters, Y, Z prime, and J, where Y define this segment Y. So all intervals considered are to the right of its left endpoint. The leftmost queried point is in this segment Z prime, and the leftmost queried interval is J. So in this case, we have to query this interval J minus 1 because it contains segment Z prime. And now let's look at what happens when we query J minus 1. If the value falls in the segment K, then we have to query the next interval from right to left, and we can follow this order from right to left because we have this proper interval graph. So the expression for L is going to be, so we have to query interval I minus 1, and we have a subproblem with, but now the leftmost query point is in segment K, and the leftmost queried interval is J minus 1. However, if the value falls in this segment K prime, then again we have to query J minus 1, but now the leftmost query point is still in Z prime, and the leftmost query interval is J minus 1. But now notice that the remaining left subproblem is totally independent from the previous queried points. So now we're going to refer to table M to solve this problem independently. So now from segment Y to Z prime minus 1. So in general, we refer to table M if the subproblem is trivial, or if the next interval in this order does not contain the leftmost queried point. Otherwise, we queried the next interval in the order, and for each possible segment for the precise value, we have a left subproblem with the updated leftmost queried point and updated leftmost queried interval. And this table can be computed in time big O of n to the 4th. So just a few open questions is if we can solve the sorting problem more efficiently, and we ruled out some possible solutions, and the complexity of the minimum problem. And other problems in the scenario could be studied, such as the median and the minimum spanning tree problem. So that's all. Thank you for your attention.
Hi, Murilo. Thanks for this nice talk.
Thank you.
Does anyone have a question for Murilo? If yes, just go for the mic in the middle of the room. If not, I have just one curiosity. Uh,
Okay.
what is the if you have my question is if you have a hint for the minimum complexity that one can achieve? Like, do you have some conjecture for that?
Uh,
Talk about the
for the
process.
sketchy problem.
Yes.
Yeah. So we could roll out some possibilities for improving. In particular, it looks like it cannot be better than n cubed
Okay.
because essentially we found a situation that you if you remove intervals, you cannot find an optimum substructure. So it looks like you cannot be better than n cubed, but we don't have a lower bound.
I see. I see. Yeah. So there's still some space for improvement. That's nice. Okay. Okay. Thanks a lot, Murilo. And if anyone have more questions to Murilo, we can you can ask in the lobby.